Welcome back, design junkies, to Mechanical Engineering Made Simple.
Today we're doing a deep dive into the structured methods that really let engineers get a handle on creating a product. We're talking everything from the high-level customer wish list all the way down to the tiniest manufacturing detail.
Okay, let's unpack this. We're dealing with systems so complex, they often just exceed our natural cognitive limits. The old way of thinking, that machine age idea of just breaking things into parts.
It just doesn't work anymore.
Right. We need frameworks to actually manage system-level complexity, to get into what some people call synthetic thinking.
Absolutely. When we talk about engineering these really complex systems, you run right up against the brain's limitations. I mean, there's that famous paper, the magic number 7, plus or minus 2.
Yeah, you can only juggle so many things at once.
Exactly. We can only really process a handful of distinct categories at one time. So to succeed in this system age, we have to have robust structures for how we think and how we document.
So the mission today is to uncover those structures, starting, I guess, right at the beginning with requirements. When we say success is baked in from the start, it means writing great requirements. What does that actually mean, beyond just being clear?
Well, the number one attribute is being solution neutral. A good requirement specifies the what the system has to achieve, never the how. And of course, it has to be concise, unambiguous, and this is the big one, verifiable.
Verifiable is a must-have. I mean, if you can't prove you met it later with a test or some analysis, it's just a wish list, right?
It is, and that's why the grammar, the language we use, matters so much. It sounds nitpicky, but it's critical. Requirements use the word shall. That's a command. It's a non-negotiable specification.
Okay, so the system shall.
Right. And then statements of fact, they use will. And goals, those desired attributes that are maybe harder to quantify, they use should. That linguistic discipline, it just removes a massive amount of ambiguity down the line.
That clarity is essential because these things cascade down through the whole life cycle, the V model. So if requirements flow down, what's the biggest failure point? Is it a vague scope at the top or maybe poor verification testing at the bottom?
The V model is designed to prevent both of those, really. It shows how requirements flow from the high level, the voice of the customer, that's your initial baseline. Then they get decomposed into technical specs, and then they're tested and validated back up the other side of the V, all the way to a verified product baseline.
So every step is like a contract.
It has to be. It prevents that uncontrolled drift.
Okay, so we've defined what we need. Now, how do we design so it's robust? This seems to take us into axiomatic design, which tries to create almost universal laws for good design using Sue's 2 axioms.
It does. Axiomatic design gives you a really rigorous framework for picking architectures that connect the customer domain, the functional, the physical, and even the process domains.
And axiom 1 is all about avoiding dependency, the independence axiom.
Correct. It states that you have to maintain the independence of your functional requirements, your FRs. And we can visualize this with a design matrix. The ideal, the perfect scenario, is an uncoupled design.
That gives you that clean diagonal matrix. One component or design parameter only controls one functional requirement.
Exactly. One knob for one function. But the real world, it means trade-offs.
Of course.
It does. So decoupled designs are often necessary, and they're manageable. That's a triangular matrix, where you can at least sequence your adjustments in a logical order. The real killer, though, is a coupled design.
That's where changing one thing just messes up a bunch of other things.
Right. It leads to endless, costly trade-offs.
The classic example is the old refrigerator, the one with a single fan for both the freezer and the fridge. You adjust one, and you throw off the temperature of the other. It's totally coupled.
A perfect example. Now, axiom 2, the information axiom, that one focuses on minimizing the information content of the design.
Which sounds abstract, but what does it mean in practice?
It just means maximizing the probability that the system will work reliably. We want elegant designs with a high probability of success, designs with less uncertainty. It's basically an argument for simplicity.
Okay, so once we have that elegant, uncoupled design, the next fight is protecting it when it hits the factory floor. And that's where critical parameter management, CPM, comes in.
That's the practice. It's aimed specifically at sustaining that system robustness all the way through detailed design and into manufacturing. So early on, engineers optimize these critical parameters. They might figure out the perfect belt tension for a paper feeder has to be, say, 15 newtons.
Right, 15 newtons is this critical functional value, but it's so easy for someone on the manufacturing side to lose sight of that if they're just focused on cost or making it faster to assemble.
That is the exact risk CPM is designed to fight.
Yeah.
It ensures that those optimized functional requirements are flowed down properly to set the manufacturing precision levels you need. It keeps the focus on the systems function, not just, easy assembly.
This flows right into the economics of all this. We've come a long way from the old gonna-go gauging culture that was just obsessed with tight tolerances for their own sake.
Oh, absolutely. The modern view is entirely economic. You select a production process to minimize the total cost. And that total cost is the sum of two things: the manufacturing process cost plus the quality loss you get from variations.
So you have to ask, is the money I'm spending on more precision actually worth the reduction in failures I'm going to see?
That's the question. And that whole framework is really built on the work of Dr. Shehart back in the 1920s, his realization that variation is just a natural part of any process.
Right, you have that natural inherent variation sigma, and then you have variation from special causes that you try to eliminate.
Exactly. And our goal is to economically manage the variation that we can't easily get rid of.
So tell us about this three-tiered tolerance approach. It's a really powerful idea that ties engineering precision directly back to the customer's wallet.
It is. It uses what's called the quadratic quality loss function to set tolerances based on cost. So the outermost limit is the customer tolerance. We'll call it delta C. If a product deviates past that point, the average customer gets so mad they call for a recall or a repair.
And that incurs a huge loss, L sub C, from all the field service and logistics.
A massive loss. So working inward from that, you have the manufacturing tolerance, delta M. That's what actually goes on the drawing.
Okay, so how is that one calculated?
Delta M is calculated to minimize the total cost. The idea is, if a unit deviates past delta M in the factory, it is cheaper to fix it right there at cost, L sub M, than it is to ship it and risk that huge field cost, L sub C. That trade-off basically defines your manufacturing window. The formula is delta M equals delta C times the square root of LM over LC.
And then there's a third, even tighter limit, the adjustment limit, D.
That's an internal factory limit. It's used in operations to save even more money by stopping variation before it even gets close to the delta M boundary. It proactively avoids the need for any factory rework.
So you're forcing everything to be really tightly grouped around the ideal target value.
That's the goal.
Managing all this complexity and variation, it often demands real innovation. What if we hit a technical contradiction, where improving feature A makes feature B worse? How do we break through that without just making a lazy compromise?
Well, that is the entire philosophy of TRIZ, the theory of inventive problem solving. Conventional engineering, you're right, it usually settles for a compromise. TRIZ thinking tries to overcome that contradiction completely.
That sounds a lot like it's aiming for the law of ideality.
It is. That's the central concept. Any technical system tends to become more reliable, simpler, more effective, more ideal over its lifetime. The ideal solution is often when the element that's causing the problem is just absent.
Can you give an example?
Sure. Imagine you're testing the effect of acids on metal specimens inside a special chamber. But the acid is also reacting with the chamber walls, messing up your results. The ideal solution is for the chamber to be absent.
How is that possible?
You use the specimen itself as the chamber. You find a way to contain the acid within the thing you're testing. The problematic element is gone.
Wow, that's a huge creative leap. This also changes how we think about reliability, doesn't it? It moves it from just a static probability to something more active, like failure mode avoidance, pushing the walls of the operating window further apart.
Exactly. And one really powerful strategy for widening that window is to create two distinct operating modes for a component.
What would that look like in the real world?
Think about a retard roll in a copier. It's a wear item. It's designed to fail eventually. The innovation was to add a tiny drag brake that only engages to inhibit rotation during a multi-feed, a paper jam.
So it's not wearing out during normal operation.
Right. It creates a special mode just for handling jams, which saves all that wear and tear during normal single-sheet feeding. It dramatically extends the system's life.
Let's pivot to testing for a second. Engineers are relying so much on simulations now, even though we all know those computer models can be flawed. So what happens when you throw a complex, statistically designed experiment at a bad model? Does that help find the flaw?
The research here is actually really counterintuitive. It turns out that when engineers used flawed computer models, they were more likely to spot the flaw using simple adaptive one factor at a time or OFAT searching.
Wait, you're saying a simpler search strategy made the human engineer better at finding an error in a complex simulation, not a big, complex statistical design?
That's what the data showed. It
Oh.
seems the complexity in the testing method actually overwhelms the engineer's cognitive ability to perceive the error in the model. Simple, step-by-step changes enhance our ability to see when something's wrong.
Okay, so what does this all mean for us? I mean, we've gone from requirements that have to say shall, to decoupling design with Axiom 1, to these economically optimized tolerances, and even designing for failure avoidance. What's the thread that ties it all together?
I think it's how quantification extends into every part of the design process, even into quantifying the uncertainty itself. Think about error propagation in a measurement. Say you want to determine the local acceleration of gravity, g, using a pendulum. The formula is g equals 4 pi squared L over t squared, where L is the length and t is the period.
So you have to measure the length and you have to measure the period, and any error in those measurements is going to affect your final calculation for gravity?
Exactly. And when you look at the formula for the most probable error, it's fascinating. The final error in g, let's call it EG, equals the square root of the error in L squared plus the quantity 2 times the error in t, all squared.
So hold on. The error in the period t is multiplied by 2 before it gets squared.
Correct, which means the measurement error in the period contributes 4 times as much uncertainty to your final result as the error in the length, L.
4 times the impact. Wow. That tells you exactly where you need to spend your time and money to get more precision in that system.
It does. It raises that critical question for any system you design. Which parameters, which measurements are truly driving the success or failure of your outcome? And where should you absolutely stop compromising and instead maximize precision?
Focus your precision where the physics actually demands it. That's a perfect final thought.